Good morning, everyone. My name is Gerson Leonel. I'm a third-year chemical engineering PhD student at Arizona State University. I work under the direction of Professor Navrosky, and today I'll be presenting to you on the pyrolysis behavior of silicon oxycarbide polymeric precursors, namely TPTS and DDTS. Without further ado, let's get started with the presentation. So current industrial challenges have fueled the research and development of materials that are suitable for heterogeneous catalysis, carbon capture, and even high temperature applications. A class of materials with properties as such includes hybrid materials. But what exactly are hybrid materials? These are materials which within their microstructure have multiple constituents or components that interact with one another, either at the nanometer scale or even at the molecular level. What makes of hybrid materials so interesting is the fact that simply by tuning their method of synthesis or even changing the relative amounts of the different constituents, one is able to obtain structures with unprecedented properties in regards to their reactivity, porosity, pore size, and even thermal stability, thus making them suitable for application in gas separation, water purification, as well as high temperature coatings. Over the past 5 decades or so, polymer-derived ceramics, also known as PDCs, have gained significant popularity. And this is exactly what they sound like. These are ceramic materials like silicon oxycarbides, silicon oxycarbonitrides, silicon carbides, and so on, derived from the high temperature pyrolysis of silicon-containing polymeric precursors. What makes of these materials even more interesting is that they tend to have a rather complex microstructure, more often than not found in a disorderly fashion, containing multiple nanodomains per se. In our current work, we decided to investigate two different polymeric precursors. More precisely, we decided to investigate their pyrolysis behavior as well as the structural evolution of their respective silicon oxycarbide ceramics. The two different polymeric precursors that we decided to investigate are TPTS and DDTS, and we can see that these polymeric precursors have rather long names. As shown in the figure underneath, the main structural variable for these polymeric precursors that have rather comparable structures is in their carbonaceous pendant groups, wherein in DDTS we do see the addition of high molecular weight phenyl groups as opposed to vinyl groups which are present in TPTS oligomers. Essentially, what we sought to do is to identify whether minor changes in the structure of the oligomers result in significant differences in the pyrolysis behavior of the polymeric precursors, as well as the structural evolution of their respective silicon oxycarbide ceramics. To study the pyrolysis behavior of those polymeric precursors, we utilized TGDSC coupled with a mass spectrometer. From TGDSC, we're able to see that these materials undergo multi-step decompositions, which is expected. But what we're also able to see is that unlike in DDTS polymeric precursors, during the pyrolysis of TPTS, we see this rather sharp decrease in mass at temperatures close to around 190 degrees centigrade. So it's interesting to see this difference. Similarly, by looking at their DSC curves, we're able to see that most of the heat flow is dominated by exothermic peaks. The peaks that we observe around 180 all the way to 400 degrees centigrades can be attributed to the cross-linking of the polymeric precursors. Similarly, the exothermic peaks close to around 600 degrees centigrades can be attributed to the ceramization of the polymeric precursors. Because we coupled the TGDSC to a mass spectrometer, we were also able to observe the evolution of gases during the pyrolysis of these materials as shown by these peaks, and the results are summarized in this curve. As expected, which is usual during the pyrolysis of siloxanes, we do see the evolution of organics such as CH4 as well as C2H4. During the pyrolysis of TPTS, we observed the evolution of gases corresponding to mass 31 and mass 40. In contrast, during the pyrolysis of the DTS, which is not observed during the pyrolysis of TPTS, is the evolution of gases corresponding to mass 32. In both these cases, during the pyrolysis of DDTS and TPTS polymer precursors, we do see the evolution of gases corresponding to mass 44, which can be attributed to the evolution of either organics or even organometallics that contain silicons, such as silenes. By that I mean silicons double bonded to carbons. Further characterization was done on the silicon oxycarbide ceramics that are derived from these polymer precursors between 800 and 1200 degrees centigrades. In all the silicon oxycarbides, we do observe the presence of D and G bands, which correspond to the presence of sp2 hybridized, disordered, and graphitic-like carbons. By integrating these peaks at their full width at half maximum, we're able to find the relative amounts of disordered to graphitic-like carbons. And what we see from our results is that with increasing pyrolysis temperature in general, we do see a significant increase in the relative amount of disordered free carbons compared to graphitic-like carbons, which is pretty interesting to see. Similarly, we further investigated the surface microstructure of these materials by performing high-resolution XPS in order to identify the bonding speciation from their Si2P, C1S, as well as O1S convolutions. And we did this for both TPTS and DDTS-derived ceramics. From our results, we're able to see that in all samples, independent of the polymer precursor that was utilized, we do see significant amounts of bonds corresponding to SiO4, SiCO3, as well as SiC2O2. Similarly, we're also able to see significant amounts of bonds corresponding to CC, CSI, C double bond O, and so on, which is expected. But what is also interesting to see is that with increasing pyrolysis temperature, we don't see significant changes in the bonding speciation on the surface of these materials. What do I mean by bonding speciation? Which bonds are or not present, as well as their corresponding domains. Instead, what we do see is a change in the relative amounts of the different bonds and their respective domains. From HRXPS of TPTS derived ceramics, we're able to see that we observe an increase in the amount of mixed bonding between 800 and 1200 degrees centigrades. And those would be bonds that correspond to SiO4 minus X, C, X. Similarly, as we look into their SiO4 bonds, which could be indicative of silica, most likely in its amorphous state, we do see a significant increase between 800 and 1000 degrees centigrades, followed by a slight decrease between 1000 and 1200 degrees centigrades. And because we don't see any convolutions corresponding to silicon carbide from their Si2P curves, it's then suggested that the SiC bonds observed from their C1S convolutions is rather representative of bonds present in their mixed bonding networks and or units. As we look into the structural evolution of DDTS-derived ceramics, we do observe significant increase in the amount of mixed bonding between 800 and 1000 degrees centigrades, followed by a slight decrease between 800 and 1200 degrees centigrades. I mean, 1000 and 1200 degrees centigrades in this case. And as for the SiO4 bonds, we do see a significant increase with an increase in their pyrolysis temperature, which is a slight difference or change from what is observed in TPTS-derived ceramics, wherein the SiO4 bonds increase between 800 and 1000 and then decrease between 1000 and 1200. For the DDTS-derived ceramics, we see an ever increasing trend in the amount of SiO4 bonds. And like is also observed in TPTS-derived ceramics, we do see that the SiC bonds are rather representative of mixed bonding SiCs rather than silicon carbide, as we don't see any convolutions corresponding to silicon carbide from their Si2P curves. In order to find the surface composition of these materials, we utilized XPS surface scans, as shown in this slide. From the results, it's apparent that samples derived from DDTS consistently have a higher carbon content independent of their pyrolysis temperature. This is likely due to the fact that in DDTS polymeric precursors, we do see the addition of phenyl pennant groups, which are high molecular weight carbonaceous pennant groups, instead of vinyl pennant groups, which are present in TPTS-derived ceramics. Similarly, in all of these materials, we do see a significant decrease in the amount of carbon between 800 and 1000 degrees centigrades, in the amount of silicon between 800 and 1200 degrees centigrades, and in the amount of oxygen between 1000 and 1200 degrees centigrades. Typically, during the pyrolysis of polymeric precursors for silicon oxycarbides, we tend to not see significant loss of silicon and oxygen at temperatures beyond around 800 to 900 degrees centigrades. Typically, these tend to be pretty constant all the way to around 1400 C, 1200 C when they begin to undergo carbothermal reduction. So the significant loss of silicon, more precisely, at temperatures even close to 1000 degrees centigrades, makes of this polymeric precursors rather peculiar. In this case, the loss of silicon and oxygen between 800 and 1200 degrees centigrades can be indicative of silicon and oxygen leaving the sample at temperatures between 800 and 1200 degrees centigrades, either as organometallics or even as organics. Now, our mass spectrometer is able to detect the evolution of organic gases that contain oxygen, as well as organometallics such as silenes, by that I mean silicon double bonded to carbons, such as mass 44, even up to temperatures close to 600 degrees Celsius. Now, although our mass spectrometer can only detect the evolution of these gases up to 600 degrees centigrades, it's likely that these gases keep on evolving even at temperatures beyond 600 degrees centigrades, but instead at concentrations that are below the detection limit of the mass spectrometer. The evolution of these gases, even at temperatures beyond 800, would then suggest that we do see the presence, or we would expect to see the presence of significant amounts of hydrogen present in the bulk of these materials, although XPS suggests that we don't see significant amounts of hydrogen on the surface of these materials. Now, in order to confirm the presence or absence of hydrogen in the bulk of these materials, we would need to run further characterizations such as combustion analysis. And that is why for our future plan, we plan on characterizing the bulk of these materials. And then after we have their bulk compositions, we'll be able to utilize high temperature calorimetry to perform thermodynamic analysis in the samples and observe how is it that their thermodynamic stability changes as their structure evolves between 800 degrees centigrades and 1200 degrees C. From this work, we're able to determine how is it that minor changes in the carbonaceous pennant groups in the oligomers actually result in significant changes in pyrolysis behavior, as well as in the structural evolution of their respective silicon oxycarbides. Thank you very much, and this is my presentation to you.